Welcome to the City of Kerrville Water Reclamation Facility. We appreciate your interest in our operation, and we hope you enjoy this information. This presentation should allow you to finish with a better understanding of the services that the City of Kerrville Water Reclamation Division provides, which is but a portion of your water bill. Our daily tasks involve the collecting of wastewater from throughout the community to a central location, the Water Reclamation Facility, and completing various treatment processes before using it for reclaimed water uses or discharge to a receiving stream. The City of Kerrville has 13 full-time water reclamation operator positions that serve this community. All operators are required to maintain an occupational license issued by the State of Texas Commission on Environmental Quality. Continuing education is also required by the State of Texas, and a minimum of 30 hours must be attained every 3 years for an operator to qualify for a license renewal. Our division can be viewed as 3 separate operations: the wastewater collection system operation and maintenance, the water reclamation facility operation maintenance, and the reused water storage and distribution system operation and maintenance, with each employee cross-trained for all components of work. Today we will be discussing what wastewater is and where it comes from, the process used by this facility to treat wastewater, and the resulting products from the treatment process. What is wastewater? We use water for many purposes. Water that has been used by domestic, commercial, and industrial users is called wastewater. It contains feces, urine, food from restaurant and home sinks and dishwashers, detergents and cleaning agents, hair and stringy material, paper and plastic products, and water. Approximately 99.9% of wastewater is just water. Wastewater must be treated to standards set by the State of Texas, TCEQ, before it can be reused or returned to the environment. These site-specific standards are what is called our discharge permit. This facility has a daily average flow of approximately 2.2 million gallons per day, with an operational or permitted capacity of 4.5 million gallons per day. We operate 24 hours a day, 365 days a year, treating industrial and domestic wastewater for both our own community as well as the City of Ingram wastewater collection system. We also serve various septic tank pumping companies. The wastewater collection system is a series of pipes and pumping stations that convey wastewater to a treatment facility. This is not to be confused with the stormwater collection system, which conveys rainwater runoff to our local streams. Wastewater lift stations. The depth of gravity sewer pipelines can at times make it uneconomical to install and maintain them. It is in those occasions where wastewater is transported by pumping to a higher elevation or using a lift station, and then returning flow to a gravity system. Our wastewater collection system consists of 8 drainage basins, over 1,584,000 feet or 300 miles of various size sewer pipelines between the sizes of 6 and 24 inches in diameter, 25 lift stations, over 2,600 sewer manholes, and this system varies in age as well as materials. The SCADA system, or Supervisory Control and Data Acquisition. SCADA refers to a system that controls and/or collects data from various devices, such as pumps, sensors, flow meters, and some treatment operations from a remote location. It then sends this data to a centralized location, which then manages, controls, and archives the data. Since SCADA monitors certain operations 24 hours a day, it can detect alert conditions at remote sites and convey those alarm conditions to the operators of the facility. enabling rapid responses to alerts from lift stations, as well as certain aspects of the treatment and reclaimed water distribution operation. The SCADA system presents various structures of monitoring that provide our staff the ability to respond to system calls, monitor emergency situations real time, and compile operational data. A little bit about our own wastewater treatment history here in Kerrville. The original wastewater treatment facility was located on Memorial Boulevard, just across from Schreiner University. It predates 1950. In 1950, the City of Kerrville constructed a larger treatment facility, which was constructed at the same location as our current facility. The former facility was a trickling filter treatment process. This process was used into the 1970s. In 1988, a new plant was constructed which included a new level of effluent discharge limitations. Nutrient removal requirements and stringent discharge permit limits that vary based on the current flow of the Guadalupe River were implemented. Since its original construction, various treatment units and equipment have been rehabilitated and/or replaced. This facility is on a continuous schedule of equipment evaluation, maintenance, and replacement. After successful application using reclaimed water at the wastewater treatment facility, additional uses for the effluent were soon realized. In the late 1990s, the City of Kerrville decided to expand the beneficial use of its treated effluent for irrigation purposes. This was the beginning of this community's reuse water program, and it has continued to expand since its inception. On this slide, we show the flows to the treatment facility. The arrow color yellow represents wastewater being treated, black represents sludge, light blue represents treated and clarified water, brown represents filtrate or wastewater created by the treatment processes, purple is reclaimed water, and dark blue is effluent discharged back into the environment. The first stage as wastewater enters the treatment facility is primary or preliminary treatment. This includes screening through the use of mechanical step screens, grit removal through vortex method, flow equalization between the treatment units and the equalization basin, and screening and grit disposal, which is taken to the landfill. The removal of grit prevents unnecessary abrasion and wear of mechanical equipment. Grit deposits in pipelines and channels, and accumulation of grit in anaerobic digesters and aeration basins diminishes the treatment capacity of the facility. Flow equalization. Approximately 10% of sewage flow is diverted to the flow equalization basin during daylight hours and returned to the treatment process during the night. The FEB is also used by septic waste companies for discharge of their waste. Some of the benefits of flow diversion are storage capacity for volume surges of influent flow, as well as an additional food source for the facility's biology during nighttime flows, since carbon sources are limited at night from lack of human activity. Without this consistent food source, the biology that is relied upon to perform the digestion of the targeted nutrients and pollutants have difficulty performing efficiently. Secondary treatment. The process used in this facility improves upon the activated sludge process through the use of anaerobic selectors to develop a biomass. This biomass stores BOD anaerobically and then assimilates phosphorus in a subsequent oxic or aerobic zone. This particular process helps its resistance against flow-related and organic upsets. The activated sludge process removes carbonaceous pollution in wastewater through two main stages. These consist of an aeration tank, or oxidation ditch in our case, where the wastewater is mixed with oxygen. The aeration tank contains mixed liquor suspended solids, which is a mixture of wastewater and recycled sludge, which acts to reseed the process. In the second part of the process, clarification, the aerated mixture of biological flux settles and eventually separates the sludge from the treated water. Nitrates and/or phosphates require further treatment for removal. The Kerrville facility uses the aerobic anoxic or AO process, which is a modified design of the activated sludge process. It allows enhanced removal of phosphorus by luxury uptake in an anaerobic environment, along with removal of nitrogen by stripping off and using the oxygen molecule from nitrates and releasing the remaining free nitrogen into the atmosphere. The addition of metal salts, known to act as coagulants, such as aluminum sulfate or ferric chloride, are used to further enhance this facility's ability to remove targeted nutrients. The name of this process is known as precipitation. The anaerobic or anoxic tanks are not aerated, and they continuously mix. They help enhance this facility's ability to remove phosphorus and nitrate. The oxidation ditch provides dissolved oxygen and helps to maintain a velocity to keep the solids in suspension. It removes CBOD, phosphorus, and ammonia. The above treatment units are the biological reactors of this facility. These units are designed to cultivate particular types of microorganisms that provide for the removal of certain pollutants within the wastewater. Operators strive to provide consistent conditions in which the desired microorganisms can thrive and ultimately oxidize a large portion of the targeted nutrients contained within the wastewater. A mixer on each basin combines the incoming raw influent with returned sludge from the clarifiers. This mixture then enters the oxidation ditch from the anoxic basins. A total of 4 mounted and 4 floating rotors provide dissolved oxygen, as well as velocity to maintain the solids in suspension throughout the basin. The oxidation ditch has a capacity of 2.08 million gallons and an average detention time of 15.5 hours. After detention time is met, the mixed liquor flows out of the oxidation ditch, where coagulants such as aluminum sulfate, ferric chloride, and cationic polymers are introduced into the flow stream to aid with the settling of solids. The addition of these chemicals also provide precipitation of phosphorus. The mixed liquor then travels through a concrete structure with control gates called a splitter box, where it is distributed evenly through clarifiers. This facility has 3 clarifiers, which enables flexibility for operation and maintenance. The clarifier allows solids to settle out of the water. The solids that are settled are either returned as RAS into the treatment process in order to reseed the biology, or they are wasted as WAS by means of dewatering the sludge through a belt filter press and removing it from the process. The cleaner water at the top then flows over the weirs and on to the next stage of treatment. Some of the factors affecting performance are hydraulic loading, the volume of solids applied, the settling characteristics of your solids, the thickness of your solids blankets, the return rates or your wasting rates, as well as temperature. I am often questioned whether the clarifier is simply a tank. It is a containment structure, but there are a few critical components that make it work. Each of these components are critical to the operation of this appurtenance. Return activated sludge. Settled solids are returned from the bottom of the clarifiers to the aeration tank. This is known as return activated sludge, or RAS. The returned sludge is intended to reseed the aeration basin with treatment organisms. It also provides a means to control the clarifier blanket levels. Sludge is returned to the aeration basin through the use of pumps. Approximately 60% of the volume of daily influent flow is returned at this facility. Waste-activated sludge. Accumulated solids that must be removed from the process are known as waste-activated sludge, or WAS. A consistent program of removing excess solids maintains the necessary balance within the activated sludge process. Failure to remove the excess solids leads to poor operating conditions and effluent permit violations. Sludge is dewatered through the use of a belt filter press. Approximately 900 dry metric tons annually are disposed of from this facility. Sludge dewatering. Sludge is pumped from the clarifier and polymer is added into the piping, where it then flows onto a permeable belt which allows water to separate from the sludge. It then goes through a series of compressing rollers that squeeze additional water from the sludge. Presented on the left is an animation of a belt filter press during the sludge dewatering process. On the right is a photo of the Kerrville landfill waste station, where sludge is transported to, composted under the landfill permit, and used for ground cover on the landfill. Tertiary treatment. Filters are controlled by a system of automation which enables automatic air scour and backwash cycles to clean the filter media at desired intervals. When the flow stream discharges from the clarifier, it then enters the filter cells. Within these filters, the collected solids become accumulated in the media, and the filter eventually loses efficiency or becomes clogged with the debris that it is filtering. During controlled intervals, automation initiates a backwash cycle. Air scours the filter cell, causing the collected solids to rise to the top level of the filter. Then, previously treated effluent water is pumped through the filter media from the floor of the filter. The dirty backwash water is carried upward into the dirty backwash chamber and is recycled back to the secondary treatment system. Once the backwash cycle is complete, the filter automatically returns to service. Filters remove residual total suspended solids in order to polish the effluent of solids that did not settle in the clarifier. It also increases disinfection effectiveness by providing additional TSS and BOD reduction. The drawing on the left shows a gravity sand filter during normal operation while it is filtering water. The drawing on the right shows a filter during the backwash cycle, which rejuvenates the filter so that it may continue filtering the water without clogging the filter media. The wastewater treatment process alone may remove greater than 95% of pathogens. Further disinfection is accomplished by the introduction of chlorine gas to the water for a prescribed period of time referred to as contact time. This deactivates pathogenic organisms which may cause diseases such as typhoid, cholera, dysentery, gastroenteritis, or hepatitis A. The effectiveness of disinfection is measured by testing for the presence of indicator organisms at the completion of the disinfection process. For the distribution of reclaimed water, a slight residual of free chlorine is desired after the specified chlorine contact time. Water that has been collected from a sewerage system or industrial process and treated to a specific standard that is appropriate for certain intended uses is called reuse water or reclaimed water. Existing reuse water customers in Kerrville are Scott Schreiner Municipal Golf Course, Comanche Trace Golf Course, Tivy High School Baseball Complex, the Soccer Field Complex, and truck-transported reuse water used for construction purposes. Some of Kerrville's soon-to-come customers are the City of Kerrville Sports Complex, River Hills Golf Course, and Schreiner University campus. These are photos of our reclaimed water storage pond that is currently under construction. Completion of the project is estimated to occur within the next 6 months. The Reclaimed Water Storage Pond project will provide approximately 90 million gallons of storage capacity of reclaimed water. It improves the ability for us to serve our existing irrigation customers with reliable delivery of contracted reuse water volumes. The project also comes with a new reuse water distribution pumping station and distribution system piping to future irrigation customers. Another benefit that can derive from this project is that it can provide another source of drinking water for the community in the future when the need arises. Dechlorination and sampling. Water that has not been reclaimed for beneficial use is discharged into Third Creek, which is a tributary to the Guadalupe River. Chlorinated effluent can be toxic to aquatic life. It is therefore necessary to remove the chlorine from the effluent prior to its discharge into the receiving stream. Chlorine is removed by introducing sodium thiosulfate with the water in dosage amounts controlled by metered plant effluent flow volumes in real time. Before being distributed as reclaimed water or discharged into the receiving stream, the treated effluent and reclaimed water volumes being discharged from the facility are measured by a flow meter. The flow meter constantly sends a signal to an automated sampling machine, which retrieves, stores, and refrigerates water samples from the stream of treated effluent 24 hours a day. The intervals between samples are based on the volume of metered effluent. Regulatory compliant sample testing is performed by the City of Kerrville Laboratory, which maintains the necessary accreditations required by the state of Texas to perform these duties. Regulatory discharge limits. There are many stringent regulatory requirements that must be monitored and complied with at this facility. This spreadsheet lists TCEQ permitted values for discharged effluent, biomonitoring, flow, reclaimed water, and sludge requirements. If you have any questions about this presentation or would like to schedule a tour of the treatment facility, please contact me at the email address shown on this slide. We appreciate your interest in our operation. Have a wonderful day.